Cosmic rays are pretty wild things. They sound like some kind of science fiction ray gun, but they're not. They are actually tiny particles moving incredibly fast, and they hit Earth all the time. Think of them as very small, very energetic messengers from space. And when I say tiny, I mean way smaller than a speck of dust. We're talking about atoms, or parts of atoms. Most of the time when we talk about cosmic rays, we're talking about protons. That's the nucleus of a hydrogen atom. It's just one tiny particle with a positive charge. But it's not always just protons. Sometimes it's the nucleus of a helium atom, which has two protons and two neutrons. And then sometimes it's the nuclei of even heavier elements like carbon or oxygen or iron. Really, it's like a whole mix of stuff in the periodic table, but mostly the lighter elements. And there are also some electrons and positrons mixed in, but they make up a much smaller fraction. So these particles aren't rays in the sense of light rays, like sunshine or X-rays. They are physical particles, actual bits of matter zipping through space, and they are moving at speeds that are almost unbelievable. We're talking speeds very close to the speed of light. That means they carry a huge amount of energy, and way more energy than we can give particles here on Earth, even with our biggest particle accelerators like the Large Hadron Collider. These super speedy particles fly through the vacuum of space, cross vast distances, and then they smack into Earth's atmosphere. They hit it hard because they are moving so fast. And what happens then is pretty interesting. They don't usually make it to the ground themselves. When a primary cosmic ray particle hits the atmosphere, it collides with atoms in the air, like nitrogen or oxygen. This collision shatters both the incoming cosmic ray particle and the atmospheric atom. It creates a whole shower of new secondary particles. It's like a tiny high-energy explosion up in the sky. This shower can involve hundreds, even thousands of new particles, things like muons, neutrinos, electrons, positrons, and gamma rays. Most of these secondary particles eventually get absorbed by the atmosphere too, or they decay into other particles. But some of them, especially muons, can make it all the way down to the ground. In fact, if you're reading this, there are probably muons from cosmic ray showers passing through you right now. Don't worry, they're harmless. We're exposed to a very small amount of this radiation all the time, and it's part of the natural background radiation on Earth. So that's what cosmic rays are: tiny, very fast particles, mostly protons, that come from space, hit our atmosphere, and create showers of other particles. But the big question is, where do they come from? That's where it gets really fascinating and also a bit mysterious. The truth is, cosmic rays come from a few different places, depending on how much energy they have. It's not just one source. Think of it like a river with many tributaries, all feeding into the same mainstream. Let's start with the closest source, and the one that makes the lowest energy cosmic rays, our own sun. The sun is a star, and it's a very active one. It constantly throws out a stream of particles called the solar wind. But sometimes, it does something much more dramatic. It has solar flares, which are huge bursts of radiation, and coronal mass ejections, or CMEs, which are giant bubbles of plasma and magnetic field that erupt from its surface. These events can launch a lot of particles, mostly protons, into space at high speeds. These are what we call solar cosmic rays. Solar cosmic rays are usually lower in energy compared to other types. They don't travel as far, and they don't have the same punch, but they can still be a big deal for us. When a strong burst of solar cosmic rays heads towards Earth, our planet's magnetic field acts like a shield, deflecting most of them. But some can get through, especially near the poles. They can cause geomagnetic storms, which can disrupt radio communications, mess with satellites, and even cause power outages. And they're responsible for the beautiful aurora borealis and australis, the northern and southern lights, as the particles interact with our atmosphere. So, our sun definitely sends us some cosmic rays, but these are just a small part of the whole picture. Most of the cosmic rays we detect, the ones with higher energies, don't come from the sun. They come from much farther away, from within our own galaxy, the Milky Way. These are called galactic cosmic rays. And for a long time, scientists weren't exactly sure what was accelerating these particles to such incredible speeds. We knew they were out there, but finding their cosmic accelerators was a real puzzle. The leading theory, and it's got a lot of good evidence to back it up, points to exploding stars. We call these supernovas. A supernova happens when a massive star runs out of fuel and collapses under its own gravity, then explodes with an incredible burst of energy. These explosions are some of the most powerful events in the universe, and when a star explodes, it doesn't just send out light. It creates a shock wave, a kind of fast-moving blast front that expands into the surrounding space. This shock wave is what we call a supernova remnant. Think of that shock wave like a giant, chaotic, cosmic pinball machine. Particles like protons and other atomic nuclei floating around in space can get caught up in this shock wave. They bounce back and forth across the shock front, like a ball bouncing between two moving walls. Each time they cross the shock front, they get a little kick of energy. They pick up speed, getting faster and faster until they're moving at almost the speed of light. This process is called Fermi acceleration, after the physicist Enrico Fermi, who first proposed it. So, supernova remnants are really good candidates for accelerating most of the galactic cosmic rays we see. The energy involved in a supernova explosion is enormous, more than enough to get particles moving that fast. And we see lots of supernova remnants in our galaxy. When we look at these remnants with telescopes, we see evidence that they are indeed places where particles are being accelerated to high energies because they emit X-rays and gamma rays that are consistent with this idea. These are like signatures of the acceleration process, but supernova remnants might not be the only sources within our galaxy. There are other extreme environments too. For example, pulsars. These are rapidly spinning neutron stars, which are the super dense remnants of a supernova explosion. Pulsars have incredibly strong magnetic fields. As they spin, these magnetic fields can accelerate particles, especially electrons and positrons, to very high energies. So they could contribute to the mix of cosmic rays, particularly the electron component. Also, powerful stellar winds from very massive hot stars could play a role, but these are generally thought to be less important than supernova remnants for the bulk of galactic cosmic rays. Now, it gets even more mysterious when we talk about the highest energy cosmic rays. These are the particles that have truly mind-boggling amounts of energy. We're talking about energies that are millions of times higher than what even supernova remnants are thought to be capable of. These are called ultra-high energy cosmic rays, or UHECRs. And where they come from is still a big mystery, a major unsolved problem in astrophysics. The current thinking is that these UHECRs probably don't come from our own galaxy. Our galaxy's magnetic field would have trouble containing and accelerating particles to such extreme energies, and also, if they were from our galaxy, we might expect to see them clustered in certain directions, which we don't. So, scientists think these ultra-high energy particles must come from outside the Milky Way, from other galaxies. These are called extragalactic cosmic rays. What kind of cosmic accelerators exist outside our galaxy that could possibly produce such energetic particles? The leading candidates are some of the most powerful and violent objects in the universe. One idea points to active galactic nuclei, or AGNs. These are the super bright active centers of some galaxies. At the heart of an AGN, there's a supermassive black hole that is actively devouring matter. As gas and dust fall into the black hole, they form an accretion disk, which gets incredibly hot and bright. And from this disk, powerful jets of plasma can shoot out at nearly the speed of light, extending for vast distances into space. These jets are incredibly energetic, and the shock waves within them, or the strong magnetic fields near the black hole, could be powerful enough to accelerate particles to ultra-high energies. Think of blazars, a type of AGN where one of these powerful jets happens to be pointed straight at us. They are incredibly luminous and certainly have the raw power. Another candidate for UHECRs are gamma-ray bursts, or GRBs. These are the most powerful explosions in the universe, even more powerful than supernovas. They're brief, lasting from a few milliseconds to several minutes, but during that short time, they can outshine entire galaxies. GRBs are thought to be caused by the collapse of extremely massive stars, collapsars, or the merger of superdense objects like two neutron stars, or a neutron star and a black hole. These events create relativistic jets of material that move almost at the speed of light. The conditions in these jets are extreme enough that they could potentially accelerate particles to the highest energies we observe. There's also the possibility that very large-scale structures in the universe could play a role. When galaxies collide or when large clusters of galaxies form, they can create shock waves that ripple through the intergalactic medium. These shock waves, though perhaps less violent than those from supernovae or AGNs, happen on immense scales and could collectively accelerate some particles to very high energies over long periods. But here's the tricky part with UHECRs, the part that makes them such a mystery. There's something called the GZK cutoff. GZK stands for Greisen, Zatsepin, and Kuzmin, the scientists who predicted it. This theory says that if a cosmic ray particle has extremely high energy and travels a very long distance through space, it will interact with the faint microwave radiation left over from the Big Bang, which permeates all of space. These interactions cause the cosmic ray particle to lose energy, so ultra-high energy cosmic rays shouldn't be able to travel more than about 100 or 200 million light years before losing most of their energy. This means that any UHECRs we detect must come from relatively nearby sources in the universe within that distance. The problem is, when we look for these nearby powerful sources in the directions where we detect UHECRs, we don't always find obvious candidates. This discrepancy is a big headache for astrophysicists. It means either our understanding of these sources is incomplete, or there's something we don't quite grasp about how these particles propagate through space, or perhaps there's a different, unknown acceleration mechanism at play. It's a huge puzzle, and it's why experiments like the Pierre Auger Observatory are so important. They are trying to gather enough data to pinpoint the sources of these elusive, highest energy particles. So, how do we even know about all this? How do we detect these tiny, fast-moving particles that are so hard to pin down? We use a lot of clever ways both on the ground and in space. For the lower and medium energy cosmic rays, the ones that mostly come from our galaxy, we use space-based detectors. These are instruments mounted on satellites or on the International Space Station, like the Alpha Magnetic Spectrometer AMS-2. These detectors fly above Earth's atmosphere, which means they can directly detect the primary cosmic rays before they smash into air molecules. This allows us to precisely measure their composition, what kinds of particles they are, and their exact energy. It also helps us study the very rare components, like electrons and positrons. By collecting these particles directly, we can get a clearer picture of their origins and how they've traveled through space. For the higher energy, and especially the ultra-high energy cosmic rays, we mostly rely on ground-based observatories. Remember that air shower I talked about? When a super energetic cosmic ray hits the atmosphere, it creates a cascade of billions of secondary particles. These air showers can spread out over many square kilometers by the time they reach the ground. So what ground-based observatories do is detect these showers. One common method uses water Cherenkov detectors. These are essentially big tanks of ultra-pure water. When charged particles from an air shower pass through the water faster than light travels through water, which is slower than light in a vacuum, they emit a faint blue light called Cherenkov radiation. Sensors in the tanks detect this light. By placing hundreds or thousands of these tanks over a huge area, like the Pierre Auger Observatory in Argentina, which covers 3,000 square kilometers, scientists can reconstruct the direction, energy, and even the type of the original primary cosmic ray particle. They can, essentially, see the shower and trace it back to its origin point in the sky. Another ground-based technique uses fluorescence detectors. When the secondary particles in an air shower excite nitrogen molecules in the atmosphere, these nitrogen molecules emit a faint ultraviolet light, kind of like a tiny flash of light. Special telescopes on clear, dark nights can detect this fluorescence light. By observing the shower from multiple locations, scientists can create a 3D picture of the shower's development as it falls through the atmosphere, again helping them determine the properties of the initial cosmic ray. And it's not just about directly detecting the particles or their showers, we also use other messengers from space. For example, when cosmic rays hit the atmosphere, they also produce neutrinos. Neutrinos are famously elusive particles. They rarely interact with anything, so they can travel straight through planets, stars, and even your body without stopping. This means they are not deflected by magnetic fields in space, unlike charged cosmic rays. So, if we can detect high-energy neutrinos and trace them back, they can point directly to the cosmic ray source, like a perfectly aimed arrow. Projects like IceCube, a giant neutrino observatory buried deep in the ice at the South Pole, are designed to do exactly this. Gamma ray telescopes are another important tool. When cosmic rays interact with interstellar gas and dust, or with photons, they can produce high-energy gamma rays. Unlike charged particles, gamma rays also travel in straight lines and point back to their sources. So, by looking at where high-energy gamma rays come from, we can identify regions where cosmic rays are being accelerated or are interacting. Telescopes like NASA's Fermi Gamma Ray Space Telescope and ground-based atmospheric Cherenkov telescopes like HESS, MAGIC, and Veritas are constantly scanning the sky for these gamma ray signals. So, why do we even bother with all this effort? What's the point of studying these invisible, tiny particles? Well, cosmic rays are incredibly important for several reasons. First, they tell us a huge amount about the most extreme environments in the universe. They are samples of matter from places we can't directly visit, like the hearts of exploding stars or the jets of supermassive black holes. By studying their energy, composition, and direction, we learn about the physics of these violent cosmic events, the strength of magnetic fields in distant galaxies, and the processes that govern the evolution of stars and galaxies. They carry information about the energy budget of our galaxy and beyond, showing us where all the power is coming from. Second, cosmic rays have practical impacts here on Earth and in space. For astronauts, especially those on long missions outside the protection of Earth's magnetic field, cosmic radiation is a serious health concern. Exposure to high energy particles can damage DNA and increase the risk of cancer and other illnesses. That's why scientists are always looking for better ways to shield spacecraft and predict solar storms, which can dump a lot of low energy cosmic rays on us. Even for people on Earth, cosmic rays have an effect. At airplane altitudes, the radiation dose from cosmic rays is significantly higher than on the ground. Pilots and frequent flyers receive a slightly increased radiation dose, though still generally within safe limits. And down on the ground, high-energy muons constantly stream through us. They contribute a small part to our natural background radiation. Cosmic rays can also affect our technology. They can cause soft errors in computer chips, flipping a bit from a 0 to a 1, or vice versa. This usually doesn't cause a major problem for your home computer, but for critical systems, like those in satellites or specialized industrial controls, it can be a serious issue. The designers of these systems have to account for cosmic ray effects. There's even a fascinating, though somewhat controversial, idea that cosmic rays might influence Earth's climate. Some scientists have proposed a link between changes in cosmic ray flux and cloud formation. The idea is that cosmic rays could help to ionize the atmosphere, creating nucleation sites for water vapor to condense around, thereby influencing cloud cover. However, the scientific evidence for a strong direct link to significant climate change is still pretty weak and debated. It's an area of ongoing research, but it's important to differentiate it from the much stronger human-caused climate change from greenhouse gases. Beyond these impacts, cosmic rays are also crucial for understanding the history of our planet. For example, they are responsible for creating carbon-14 in the atmosphere. When cosmic rays hit nitrogen atoms, they transform them into carbon-14. This radioactive isotope is then absorbed by living organisms. When an organism dies, it stops taking in carbon-14, and the existing carbon-14 slowly decays. By measuring the amount of carbon-14 remaining, scientists can determine the age of ancient artifacts, fossils, and organic materials, a technique known as radiocarbon dating. So cosmic rays literally help us date history. And there's another curious puzzle related to cosmic rays, sometimes called the cosmic ray paradox. If you look at the elements in cosmic rays, you find that some lighter elements, like lithium, beryllium, and boron, are much more abundant than they are in the universe generally. This is strange because these elements are not easily produced in stars, but there's an explanation. It's called spallation. When heavier cosmic ray particles like carbon or oxygen travel through space, they can collide with interstellar gas and dust. These collisions can literally chip off pieces from the heavier nuclei, breaking them into lighter elements like lithium, beryllium, and boron. So the overabundance of these elements in cosmic rays actually gives us clues about how much matter cosmic rays have passed through on their journey to Earth, acting like a cosmic mileage counter. So cosmic rays are these tiny, incredibly fast particles that constantly bombard our planet. They come from a range of places: our sun, exploding stars within our galaxy, and likely from even more violent sources like active galactic nuclei and gamma-ray bursts in distant galaxies. We study them with a mix of ground-based and space-based detectors, as well as by looking for their secondary messengers like neutrinos and gamma rays. There's still a lot we don't know, especially about the highest energy cosmic rays. Their origins remain a profound mystery, pushing the boundaries of our understanding of the universe's most powerful accelerators. But every bit of data we collect, every new theory we test, brings us closer to unraveling these cosmic secrets. They're more than just bits of matter. They're vital clues in the grand cosmic detective story, telling us about the birth, life, and death of stars, galaxies, and the very fabric of space and time.